Example 1. Using a 0.05 significance level, test the claim that the three categories of blood lead level have the same mean IQ score. Does it appear that exposure to lead has an effect on IQ scores? Use the Excel output of a one-factor ANOVA test below. And this one-factor ANOVA test is the same as a one-way ANOVA test. And so we are testing this claim that exposure to lead has an effect on IQ scores. And so let's set up our null and our alternative hypothesis. And we know that our null hypothesis is the statement of equality. Because we have three different categories, I'll say that the mean of sample 1 or category 1 is the same as the mean of category 2, which is the same as the mean of category 3. For my alternative hypothesis, we said that this is not going to just be this null hypothesis, but with with these inequality symbols, because we don't need all three to be unequal. And so the way that we'll write this is that we'll say the alternative hypothesis is that at least one of these means is different from the others. All right. And so we've got a lot of information we don't need. We've got this MS, and that stands for the mean of squared error, and SS, the sum of squared error. And these are used for different types of tests that aren't going to concern us now. So here we have our degrees of freedom. Now, technology is going to calculate these degrees of freedom for us. And we have our F, our p-value, and our F critical. So our F critical, we remember, this comes from that level of significance. So this F critical is for an alpha of 0.05. And also from the fact that we have a degree of freedom of 2 and then a degree of freedom of 118. And this F test statistic comes from our data. Now, we know that this is a right-tailed test, right? And so although we don't know exactly what this distribution might look like, let's say it looks like something like this. Now, I know that my F critical value is 3.07. Let's put that over here, 3.07. And my F test statistic is 2.30. So 2.3 is going to be left of 3.07, so 2.30. And I can use this kind of idea of the rejection region, or the critical region, to determine that this test statistic is not within the critical region, and so I'm going to fail to reject my null hypothesis. The other way to go about it is with this p-value method. I know that my p-value is greater than 0.05. Because my p-value, I'll say, is p-value less than or equal to alpha? No. My p-value is about twice this level of significance. And so this is going to lead me to fail to reject the null hypothesis. Great. So I'm failing to reject the null hypothesis. Okay. But this doesn't really tell me much about my claim. Does it appear that exposure to lead has an effect on IQ score? So let's think about it. If exposure to lead does have an effect on IQ scores, then wouldn't the mean IQ scores from the different lead levels be different? If at least one of the means is different, this means that exposure to lead has some sort of effect on IQ scores. And so with my alternative hypothesis being the claim, remembering that I want to restate my final answer in terms of this claim, if I'm failing to reject the null hypothesis, then there is not sufficient evidence to support the claim. And then I'm going to restate the claim that exposure to lead has an effect on IQ scores. And so in this example, we were already given this output. And again, we're going to find this stuff using technology, but what if we're not already given the output? In example 2, we just have the raw data. So listed below are attribute ratings of males by females who participated in speed dating events. Use a 0.05 significance level to test the claim that the females in the different age brackets give attribute ratings with the same mean. Does age appear to be a factor in the female attribute ratings? So let's start to look at our original problem. Well, we have a 0.05 significance level, so we can just put alpha as 0.05 if we know nothing else. We know that in any specific situation, our null hypothesis is going to be that these means are equal. Because we have 3 different categories, so this is category 1, ages 20 to 22, category 2 from ages 23 to 26, and category 3, 27 to 29. And so our null hypothesis is going to be that all of these means are equal. And this means that our alternative hypothesis, like in the last problem, is going to be that at least one of these means are different. So at least one of these means is different from the others. Now, before we go any further, let's see what this means in the context of our problem. So we want to test the claim that females in the different age brackets give attribute ratings with the same mean. So what we're saying is that in these three categories, the attribute ratings have the same mean, are the same. And so this means that our claim is going to be this null hypothesis. So this is our claim, that despite what age group these women are in, they're going to give attribute ratings that are essentially the same, with the same mean. Okay. And now we can finally go about finding our p-value or our test statistic. We know we need an f-test statistic, and we know that this needs to be found using technology, and so here's what we are going to do. We're going to put this data into the lists of our calculators. So we're going to put this in lists 1, 2, and 3. And so I can do that by going to Stat and then Edit. And let me clear out these existing lists and just type in this new information. All right, so now that we've got all of this information typed into our calculators, we're going to go to Stat, over to Tests, and we're going to find ANOVA testing, and this is the last item. So item H, ANOVA testing, and press Enter. And then inside of this ANOVA testing, we're just going to type in our 3 lists in order. So list 1, list 2, and list 3. And I see this little blue list 1, that means I can type second 1 for list 1. And I need to separate all of these with commas. So list 2, comma, and list 3. And enclosing this with parentheses. Now our calculator is going to do all the rest of the work. It's going to perform calculations. It's going to find all the degrees of freedom that we need, so the 2 different degrees of freedom, and it's going to give us this f-test statistic and our p-value. And so if we press Enter, we get f, this f-test statistic, this p-value, and then some of this other stuff that we really don't need for our purposes with this type of test. And so if I look at this f-test statistic, 0.232, I can see that this is relatively small. I know that this is going to be positive. I can say that it's relatively close to 0. But this doesn't really do much for us unless we have the f critical value so that we can compare these two. And so we're just going to look at the p-value for this reason. My p-value of 0.794. Let's write this down. I found a p-value of 0.794. And I found this in my calculator using going to tests and then using ANOVA with the information in my 3 lists. Okay, this is a very high p-value. All we're really doing is comparing this to alpha, but because I can see that p, if the question of p is less than or equal to alpha, this is certainly not less than or equal to alpha. This is very close to 1. This means I am definitely failing to reject the null hypothesis. And in this case, my claim is the null hypothesis. And so if I'm failing to reject the null hypothesis, then I can say that there is insufficient evidence to reject the claim. And then I always want to restate that claim so that females in the different age brackets give different attribute ratings with the same mean. And I just want to point something out here that's kind of interesting. With this claim, if my claim is the null hypothesis, then there's no way I can actually have sufficient evidence to support the claim. I can either make the decision to reject this claim or I'm just failing to reject this claim. So even though our claim might be correct, with this setup, all we can do is either reject it or fail to reject it. So whenever you are performing an experiment, just make sure your claim is the alternative hypothesis so that you can actually support it.